So welcome back, everybody. I hope you had a nice break. I promised you before the break that I would talk a little bit more about the Miller effect and what it means. Up to now we looked at the formulas, but now let's look at it graphically. So the thing I wanted to show you is the following about the Miller effect. If I go back to the transfer function here, then you see that the term we get around here is a second order transfer function. It has a zero, but it also has two poles. And these two poles, as long as the CC is not there, I mean, we know them from above, then it's just the thing without the compensation capacity, this very simple transfer function. So I have one pole at one frequency and another pole at another frequency. And now there's a curious way to draw these things. And this is with a frequency axis in this way and the CC axis in this way. Double logarithmic. And normally, when you read one of those graphs, it would be this axis that varies, and on this axis you would draw the result. But in this graph, it is this axis that is the input, and here I draw the result. And what I draw is where the poles are lying. I have to close that again. And I have started with some component values here, and this means that if I have no CC or a very small CC, so this is 10 to the power of minus 18, let me make that much larger so you can see it better. So this is 10 to the power of minus 18 here. Oh, wrong tool. 10 to the power of minus 18, okay? So nothing. And in this case, with the components values I chose, both of the poles are in the same location, around a frequency of 10 to the power of 8. Yes. And now, if I increase CC, there is some capacitance around here where things start to change. And the output pole, if I increase CC, it will go up, and here it will go down. And the input pole, the one at node 1, if you increase the CC more and more, so this is 1 picofarad, 100 picofarad, if I increase that more and more, then it will just go down, 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 down. The pole at the output, when I increase CC, will go up, but not indefinitely. At some point, it will not be able to go higher. So the more additional capacitance I put there, the more I split the poles, so they will move apart. And now, if you remember your feedback theory stuff, like phase margin things from stability theory, then you will remember that if you have two poles close together at the same point, this will cause you an immediate phase change of 180 degrees. So you will get from 0 degrees phase to 180 degrees phase. So if two poles of an amplifier are very close together, you will lose all of your phase margin, and it is not going to be stable. If the two poles are very much apart, then you can make it stable, because the first pole will cause a roll-off in the frequency, and when the second pole comes, you are already beyond unity gain or something like that. So pole splitting, which this is called, you can achieve by having a capacitance between the output and the input. There is one there anyway, so it's this CDS1. But if you increase that, then you just split the poles apart further. There is a price to pay, because there also comes a zero. Yeah. So, of course, the zero equation, it was very simple if you look at it. So, if I look at the equation for the zero here in the numerator, from the Miller effect part, this I do not even have to explain, I think, that this part here in the, can I show it somewhere? Here in the numerator, this here will be a simple transmission zero at some frequency. And if I increase CC, it will get lower in frequency. This is logical, so it does that. And now you may say, yeah, yippee, a zero is a good thing because a zero increases the phase again, so I get more phase margin. But that's not the case here, because this zero is lying in the right half plane. So if you look at this here, the Laplace transfer function in the numerator, it is minus s something plus something, so this is a right half plane zero, and the right half plane zero also causes you phase loss. Now this is not something you should concern yourself too much with in this lecture if you do not know it yet, because I will not go deeper here. We will look at phase and stuff later when we go back to filtering and other topics, inductor simulation. But here, if you do not know what the phase margin is or so, then just don't care too much right now. You will not need it for your exam in this lecture. This is just to build a bridge to all of the other lectures you might have about the design of amplifiers or the stabilization of amplifiers or feedback control systems. Okay. Good. So this is what happens. But maybe you wonder whether you can only derive it or whether you can already see it a little bit better from in an intuitive way that this pole splitting is going to happen. So before I continue with other things, I will now explain to you the pole splitting in an intuitive way. I take this here and put it into my live notes. Okay. So in general, we have this situation here in the Miller effect. Now, what does it mean here? This is an amplifier, and the amplifier has a gain, doesn't it? The gain is negative. We calculated that before. Very many one-transistor amplifiers have a negative gain. So from here to here, you have a negative gain of AV, minus AV, so minus some voltage gain. And this is actually, if I use these compound values here, just minus Gm divided by G2. So the higher the transconductance, the more gain you have, the lower the output conductance. So the better your transistor current sources are, the more gain you have. But that means that if an observer, like is now sitting in this node, so imagine you stand here, and you are looking into this node here. And now somebody operates the circuit and you see here a delta V. So the voltage changes by something. Then at this node here, the voltage changes by minus the voltage gain, delta V. So the voltage drop over this capacitor is now the CC comes later. It is difficult to delete something here. Yeah. So the voltage drop here is delta V times 1 plus AV. So the charge that disappears into here, delta Q. So charge delta Q that disappears into that CC is simply the capacitance times delta V times 1 plus AV. Let me reorder these terms. But the observer, small observer who is standing there, the observer doesn't know what comes behind. All the observer sees, I have a voltage change, delta V, yeah, and I have a huge charge disappearing into that node, the delta Q. So that guy calculates it as follows and says, oh, I have delta Q divided by delta V is the the capacitance IC, and this is CC times 1 plus AV. Or in other words, what that guy sees at this node is not the capacitance itself, but the capacitance scaled by the gain of this amplifier. And that is reflected in the graph I showed you before. So this capacitance has much more influence than you believe. So if you think that it is not a problem, that you have a CDS in one of those amplifiers, because the CDS is 10 times smaller than the CGS, and then you have a gain of 50. Suddenly the influence at this node of the CDS is 5 times higher than of the CGS because of that scaling here. And that's an intuitive explanation of what you see in this graph here. So if I look at the graph again, that's an intuitive explanation of why the lower pole frequency, the pole frequency in node 1, will actually be inversely proportional to CC, and why CC dominates so much. It just is scaled with the gain of the amplifier. But why then can FP2 not get as large as it wants? So why does this not go up as far as it wants then? And there could also be an intuitive explanation of this Miller effect. I copy this slide. So the second part would work like this, that you say, okay, now I want to know what happens at the node 2. Not good. I need a bit more patience to delete it. So now I'm putting an observer here at the node 2. So what does the observer see here? What the observer sees here is that, if he looks into the node 2, is that the pole frequency depends on the conductances of these two. So the omega P2 you see here at this, just at this node, would be G2 over C2. But now suddenly some current disappears here in that direction. It also comes back through the feedback, and this means that the more CC you have, the lower your effective impedance goes. So the output, the effective output conductance will rise. So you will get more stuff happening because of the feedback. And in the extreme limit, what is a CC that goes to infinity? If you really bring it to the extreme, it is a short circuit, isn't it? So the short circuit, if you have this situation, then suddenly at the output you have that circuit we know before, which is the equivalent of a resistor. And then suddenly this resistor GM is hanging there in the extreme, and your pole frequency 2 becomes that, and that's the limit. You cannot go higher. This is the reason intuitively why that goes up here from Could I please write? Apparently not. I think I have to restart the tool. Yeah, now I can write again. So this is why the whole thing here at the output goes up from this frequency, which is G2 over C2, to this frequency here. So this, which is G2 plus Gm over C2. Okay. But not higher, because higher would mean that the whole Gm with its feedback would need to be better than just. I don't know what I wanted to say. Basically, if you do the full feedback, it is like a resistor of the conductance Gm, and that is always there. If you want the output pole to go even higher, you would have to need more conductance there. But where should it come from? I mean, the Gm is limited; it is not higher than it is, so there cannot be more conductance. This Miller effect is. Depending on how well you want to understand it, it can be quite complicated. But the essence is simple. Just because you have a capacitive feedback between the output and the input of an amplifier means that the poles will split. And this pole splitting is used quite a lot in the stabilization of different amplifiers. More questions about that? There's also presently no questions online. But that was by far the most difficult thing I told you today. It is not the most complex thing, because that may come now. It's the next example in the lecture notes. It may seem off-putting to analyze a full amplifier like this. So how would you even do that? This is a so-called OTA, an operational transconductance amplifier. And this is the same as if I draw the symbol like this here. So I would have a Gm, and here I would have a Vout with a CL, load capacitance. But now I have a positive and a negative input. So we have drawn these things before, just like blocks, ideal blocks. But now you see on the left one example for a transistor circuit which actually achieves that. And there are different ways to design that, but normally what people do in the simplest one is that they say these transistors have the same size, these transistors have the same size, and these transistors have the same size. Then in the bias point, they also have the same gate source voltages and everything, so you can say all of the middle transistors have the same GM, GDS, and CGS. All of the lower transistors have also the same as each other, and all of the upper ones also have the same as each other. Then you can start to analyze that with the driving point signal flow graph. By the way, that one here is a current source, the bias current source. Now the whole analysis here will become quite difficult if you do not know how to deal with differential circuits and common mode circuits. But that you saw already in the video. If you watched that video, I explained there what is the difference between differential and common mode circuits. I made an error in the common mode, this I will tell you later. But here I would just like to reiterate how to analyze it in the differential mode. So if you have already decided that you want to look at differential input, then you can simply say that you have here differential voltage. So half of the differential voltage is at this node, and half of the differential voltage is at this node. So the difference between V1 and V2 is actually Vd. And under these conditions that you have a symmetric circuit which you operate differentially in small signal, you can replace the common nodes by a connection to ground, small signal. This is just small signal. But now how to put that into the driving point signal flow graph? So the way I do that very often, or always, is first I think about where I should put the magic sources. And that's unfortunately very easy in this circuit, because however you look at the circuit, you just have the ground connections or supply connections here, but none of the transistors actually contain voltage sources. So all of the nodes need magic sources. So I can already go and say, okay, node 1, 2, okay, 1 and 2 have voltage sources. They are driven by the differential voltage, but node 3, node 4, node 5, node 6, they all need magic sources. So I can quickly draw all of them. So, I don't know what my computer is doing, but it must be important because it eats so much computation power. So let's make a new file here. So what I had in the middle is the V1 and the V2. And I tried to do it approximately the same as I have it in the circuit. V1 and V2, they are driven by the same differential voltage, Vd. It's just that Vd is half of it is on V1, and the other half of it, negative, is on V2. So, minus 1/2. Maybe put that on this side. And this is the differential voltage Vd. And then, this is the input, how I distribute it differentially on the left and on the right. And then I take the node 3 and the node 4. They are on the left and on the right at the bottom. And then, because they have magic sources, they will have the 1 over Y3 and here 1 over y4. I save this as OTA. By the way, since I'm happily saving stuff, have all of you realized that I always upload this on the same day? Good. Just to make sure. And then I have at the top of the circuit here, I have the node 5, which also has a magic source on it. So going back, I call this I5 and V5 with a Z5 with a 1 over Y5 in between. And now I also have the output here, also a magic source with a load capacitor on it. So I put the output, which is I6. V6 with between 1 over, very systematic, the whole thing. All right, save. And now, what is missing is simply, I mean, I could now put in all of the driving point admittances. This I may not even do. That's not the point here to go through the full analysis. But the important thing is now what are the conductances, the transconductances are going to do. So I look at every individual transistor. So the first transistor here is that one. So if I look at this here, I will get a controlled current into the node 3. And while you can always draw the equivalent circuit and think about what the source is doing, what I find considerably simpler is that if you do the source superposition, when you fill out the graph, is that you just say, okay, I take this node and I increase the voltage. What happens? Yeah? If I increase this voltage, this is a PMOS transistor, so it has less voltage difference across the controlling part, so less current. And the current flows down. You have less current flowing down, so you have a minus GM in the transfer function. So this is the minus GM1. And also here, it is completely symmetric. And I said that the two transistors are supposed to have the same GM, so they are matched, as it is called. Okay. Then I look at the next transistor. So here I have that transistor. And now there I have both options which I can do. One option is I put this transistor into the driving point impedance as a GM, because this here looks just like the feedback situation I told you. Or the other option, which I will use now, just because it is funny, I could also say this is a source. So if I increase that voltage here at this node, then more current is going to flow here. So the other option I have of drawing this into the graph is that I put from V3 to I3, but please on the other side here, I put the minus GM2. Do you agree that I can also do that? Yeah, there's some people not. And the same on the other side. you will see in the end why I was doing this. There is a reason. Just bear with me. Okay. So next transistors. Next transistor is that one. But this is the same situation we have seen many times. So from V3 to I5, we have the GM2. And also from V4 to I6. Same situation. Next transistor. That would be this one with the feedback. From V5 to I5, same argument as down here. But much more compact, please. This is minus GM3. And then the final transistor, which is this one, from V5 to I6. Minus GM3. If I did everything right, this should now be the correct thing. Now, as opposed to what I did in the lecture notes, I will now have loops. In the lecture notes, I got something without loops. There I argued if you do it in the right thing and build it into the driving point admittances, then you will not get any problems with some loops. But let's see what the advantage of this one is. If I now take this here and calculate the Mason gain and put that into my worksheet for the operational transconductance amplifier, a 0.5 I get. Yeah, it is not really nice what I get. But now we have to look a little bit more into it. So all the GDS would now come into it, but this is not as simple as it could be for a very simple reason. We have not yet used the symmetry of the whole circuit. So how to use the symmetry of the whole circuit? That would be if I look at at that here, then you see that the situation at the node 3 and the situation at the node 4 is exactly the same. So there is, if the transistors have the same size, there is not the slightest difference. So I can at least say that Y3 and Y4, the two driving point admittances, must be exactly the same. So let's see whether this becomes a little bit simpler if I do it like this. Yeah, and already I start to get a very nice result. And now I should start to put, I could start to put some content into it. Yeah. But what you already also see is that, again, if Y5 is in any way capacitive, which it will be, then I will get a 0 again. And one of the main things about systems like this is that when you get two zeros or transmission zeros is that, how shall I put it? Any of the paths through this system cannot have transmission zeros. If you look at the signal flow graph I have drawn here, the only thing you have is you have one forward path going this way, yeah? And this forward path just has poles, doesn't it? And I have another forward path, and this forward path also just has poles. Mm-hmm. And the only thing that could cause any zeros is that one path has this and the other path doesn't. Okay. So this means that in one path we have an additional pole which gives you a low pass filtering, and in the other path we don't. So let me go to a very simple signal flow graph and see what happens if I do that. I do a new one, and now I just look at this situation without naming it, and naming it, so this is just a 1. And now I say I do one path to the output, and here I just have half of the signal going here, and in the other path to the output I also have half of the signal going, but this half of the signal is now multiplied with a low pass filter. The low pass filter would be an omega p divided by S plus omega p. Mm-hmm. So that's it. Thanks for telling me. Somebody paged me and told me I forgot to switch. It will help the people online tremendously if I show them what I'm doing. But I'm very proud of myself, really. This was the first time I did it wrong today, I believe. Okay, but problems will happen. So what I have here is from somewhere in the graph, I have one branch which doesn't have a pole in it, and the other one has. Mm-hmm. Just some pole at some frequency. So I call this two paths. Mm-hmm. Yeah. And so if I now generate the Mason transfer function from the input to the output here, and I bring that back into the calculation. Mm-hmm. Let's rename that. I will definitely not calculate that, so two paths, is it? So if you have that, what you now see, if you have those two paths, is if you solve it, that you will still have the pole frequency, omega p, but you will also get the transmission 0, which is at twice that frequency. Maybe if I omit this 1/2, I mean, if we do a differential thing, half of the signal goes one path and the other half of the signal goes the other path. So if I just say, let's put it like this here, not make the 1/2, it is then wrong by a factor of 2. But the result will be much clearer. If I do it like this, generate Mason again. Overwrite, calculate again, so it is now much clearer, the result, because the factor of 2 is not in it. And this actually always happens. So whenever you have any system which has two ways going to the output, and you have one part of it that of the system, one path will contain a pole that the other part does not contain, you will automatically get a 0 at twice the frequency. Just like that. It's the difference that happens. And that is what you read in many textbooks which do not use the signal flow graphs, that people will give you the ad hoc method of saying, yeah, please go into the circuit here and look at all of the nodes. The thing you should have realized by now is that if you do the first analysis, all of your driving point impedances will appear in the denominator. So what most analog designers do is they say, okay, I look at the situation at this node. At this node, I have a GDS 2 plus a GDS 1. These are these two resistors here, plus the two gate source capacitors of those transistors. They are both CGS2. And I can just look at this expression, and I already know where one of the poles of my circuit are. And if the pole, like the one up here at the node 5, is only in one path, then yes, you also get the pole, but you also get the zero at twice the frequency. And like this, an experienced analog designer will be very fast in estimating what happens. You have to be careful, of course, when you do these short circuits, because these short circuits do not take into account that you may have some feedback around everything. And so this ad hoc method is okay, but not always. For example, we saw one counterexample here when we just looked at the common source amplifier. This gives me the chance to put it back on the grid. Yeah. When we looked at the common source amplifier, we just got the signal flow graph like this, which was straight, and the poles were where they belonged. And then I included the Miller effect in the common source amplifier. So this is more or less the same thing, but now suddenly I have a feedback, and you saw that the feedback gave the pole splitting. So the poles are moved by the feedback, they are moved apart. And this ad hoc method of saying where the poles go, this is totally okay as long as you don't have feedback. So this would be where the poles are before the feedback is taken into account. Yeah? But the feedback can, of course, always change it. So you have to be careful if you want to do the ad hoc guess of where the poles are lying. Of course, the analysis with the graph will always tell you the truth. So that was a long story about the signal flow graphs. It was also a reiteration of the video number 11. And before, in the break, a student told me that I have made a very stupid mistake in the video number 11, which I don't think I can correct anymore, because I don't have the production files anymore, but I will just write you an email about that error and will include it in the video. If you look on my video channels here, you will normally see, for example, in the video 3, I already have a longish list of beware. So what are the errors I made in the video? So in the video number 11, I will probably also do that. It is very, very small error just at the end of the video, which will confuse you if you watch the video very attentively. Yeah. But that is about the time I had for today. Time is running out. I did not cover everything, because not everything is there for everybody. The rest here of this, like how you do the gain enhancement with having cascades and regulated cascades or so. Sometimes I teach that, but these things here, they are more there for experienced or for people who really want to do analog transistor design. So this now brings me one more time to your strategy you could do in the exam or so. I'm more than happy if people can draw a signal flow graph from a transistor circuit and answer some simple questions orally. Yeah. But a cascade circuit, which gives increased gain or so, is mainly interesting for people who actually want to design analog amplifiers. So all you other people here, you are interested in the system level, or there are machine engineers here, I believe. There are biotechnicians here. So it is a very diverse customer base I have. And for them, please don't study this. It's very complicated. But if you go into the analog circuit design lectures also, and you see these things here and say, no, I really want to understand the small signal analysis, then here you have the solution of these things. So that's my recommendation. This is also why I have stopped teaching that here in the room, because I have found out that only about 10% of the students actually care about that, and nobody ever chose it at an exam. So anyway, how you think about the circuits, how you think about the feedback and about the graphs is much more important anyway. Does anyone have final questions here? Something you want to know, something you should still explain? I check again the chat. The chat is very funny today. Yeah. That was a very good point to page me. Nice that you remembered. I forgot to explain it again. Very good. It seems we have finished for today. So this was the very hard transistor thingy. The very hard transistor lecture. So I hope you enjoyed that, even those who don't normally do transistors. Now you have the hope that if you ever have to do transistors, you can deal with it in the same way you can deal with every other circuit. There was one student who also told me, wow, I'm exaggerating, sorry. Wow, your video number 12 was really hard. I didn't really get that one. This was brutal. I agree. The point with the video 12 was an outlook of the things you can do with the signal flow graphs. And actually, in this term, we have 3 full lectures to cover what the video 12 was. So if you watched the video 12 and thought, oh my God, how can I ever understand this? You will have 6 hours explaining me video number 12 to you. So don't worry right now. The video 12 was intended as an advertisement for switched capacitor circuit designers who think, could I also touch that? Yeah. But you will have 6 hours about that. So, and then is definitely sufficient. So next time we go a little bit more into back to normal circuits, an op-amp with a little bit, and then you will understand, if you don't know it yet, why it is always a bad idea to use an op-amp to drive a capacitive load. So looking forward to that, and have a nice week. Bye everybody.